So today we're going to cover what I call complex thin-walled structures. So far we've done very simple structures. We've done C-sections and rectangular sections. Everything is nice and simple, single cell, open or closed problems. In reality, wings and fuselages are not that simple. There's more complex geometry, especially wings. We often have a leading edge, a front spar, a wing box, rear spar, and then something happening rear of the rear spar. And so we've got these multicellular structures. There's some parts that are open, some parts that are closed, and we need to know how to handle those complex situations. So that's what we could call today's class wings, I suppose, as well. A lot of the content is taken from the wings section in Megson. So the first thing we've got to learn how to handle is combined open and closed sections. So what happens if we've got an open section tacked onto a closed section? How do we work out the shear flows? And it might be something that looks like this. So we've got a closed wing box at the front and then some open section at the rear that might be a shroud around where a control surface is moving. But if we were to try and calculate the shear flows in this problem, we run into an issue with our previous calculation. We don't really know what to do when we get to these junctions because we have an equilibrium equation, but we haven't applied it to something as complex as this so far. The first thing we need to understand is what happens at a junction. So how do we calculate equilibrium in this sort of scenario? Now, let's just, for argument's sake, assume we've got a shear flow in this panel of Q1. And I don't know exactly whether this lines up with the notes or not, but you can make modifications to the notes if necessary. In this panel of Q2, and in this panel of Q3. And in the middle we've got a boom. And on that boom there are some stresses. Stress. And that boom has an area B, say. Okay, so in the notes, you can follow along if you'd like. I think the diagram I've drawn is slightly different, but the logic is the same. We have an equilibrium equation that can help us here. Normally, in the problems we've solved so far, we wouldn't have had one of these panels. We would have only had two panels, and we would have said that, say, Q2 minus Q1 where Y is the Y location of that boom. Now we've got a third shear flow in there. We've got some other part that we have to add into the equilibrium, and technically we could have 4 or 5 or 6 shear flows all acting on the same boom if we had a very complex structure, but in practice 3 is the most we ever have to deal with. If we take the boom by itself, acting on the boom according to our diagram up there, and I'll use the notation that I've got up there just so that we can follow along. The shear flow in this panel, on the edge of the panel, is acting towards the front of the board. So the reaction force that it applies to the boom is the other way. So we have a force on the boom which is equal to the shear flow times the length over which it's acting. And I haven't marked the length on the diagram, but the length of the section that we're looking at there. Now, for Q2, which way is Q2 going? Well, on the edge of the panel, it's acting to the back of the board. So on the boom, it's acting forwards. And Q3, well, on the panel, it's acting backwards. So on the boom, it's acting forwards as well. Is that right? Yep. And on one end of the boom, we've got sigma B, because we've got a stress times an area, gives us the force. And on the other end of the boom, we've got sigma plus d sigma dz, or okay. So there's a change, a stress plus a change in stress as we've moved along times the distance that we've travelled. So sum of forces equals 0. We've got sigma plus d sigma dz. Sorry, I need a B in there as well. Now, we've got a plus Q3L plus Q2L minus Q1L equals 0. Okay, and we can rearrange that. The sigmas cancel out. And we end up with, on one side of the equation, we end up with Q1L minus Q2L minus Q3L equals d sigma dz L B. And all the L's also cancel out. And we end up with some relationship between the shear flows and the change in the stress as we move along. Now this bit here, we've seen that a bunch of times before. That's the thing that expands into that phenomenally large SY IX minus IXY term, the big complex term that falls out. Okay. But in the simple case where we've got a symmetric problem and that's only got a Y shear force, then this collapses to the thing that we are quite familiar with now, to minus xy on ix x by. So what we're seeing is on the left we've got some shear flows, and on the right we've got this familiar term that's to do with the boom area and the y location for the boom. Now how do we know what the signs of these shear flows should be? Well, it's really like, the reason we call shear flow is it's a bit like current flow or water flow. We can think about a direction of travel of the shear. And if we looked at this problem end on, hang on a second. I think I may have got some minus signs around the wrong way. Okay. I need to put a, that's a minus sign. So this equals that. If I put a minus sign there, I can make these plus signs. I have, okay. I've just got some minus signs around the wrong way. The notes are correct. Okay. Now, the minus signs and the plus signs come from whether we're going towards the boom or away from the boom with our shear flow. So Q1 in this case is going towards the boom, so it gets a minus sign. Q2 is going away from the boom, so it gets a plus sign. Q3 is going away from the boom, so it gets a plus sign as well. So in a problem where we didn't have a boom area, in a problem where we've just got panels connecting to one another, like we would have done before we'd idealized the structure and we were calculating integrals instead of sums. In those sort of problems, this bit just goes to 0. And you can see that the sum of the shear flows coming in has to equal the sum of the shear flows going out. So just like current flow, if we were doing it with a non-idealized structure, sum of shear flows going in equals sum of shear flows going out, just like a joint in an electrical circuit. Once we put the idealized boom area in, we need to make some slight modifications. To account for the force in the boom. But this gives us the ability to handle intersections in our problems. A lot of problems we can cut in such a way that intersections aren't that problematic, but we can't always. So I'll show you an example of how this is applied. So let's go back to thinking about this problem for a second. We have a closed section here, which we know is very good at reacting torque, and an open section connected to it, which we know open sections are not very good at reacting torque because you can't set up a shear flow that goes all the way around the loop. You have to react torque via couples of shear stress. And so they have a reaction to torque which is many orders of magnitude lower than the closed section. So what we tend to do when we're looking at torsion, if we've got torsion in a section, we only assume that the torque is carried by the closed section of the beam. So any torque is reacted just by the closed bit itself. And if we need to calculate rate of twist, then we can do so by summing the torsional rigidities of the open and closed sections. But as we'll see in practice, the closed section has a torsional rigidity that's many orders of magnitude higher than the open section, so we can normally neglect the open part. And there's a little bit more detail in Megson if you want to follow along. For shears, because the open and closed parts react differently to torque, we actually have to apply all our shear forces at the shear center. So if we have a shear at a general place that's away from the shear center, what we do to simplify the calculation is we apply a shear force at the shear centre and an equivalent torque to have a force system that's the same as it was before. So in a general shear problem, we have to apply a shear force at the shear centre, work out where the shear centre is if we don't know that, and then apply a torque to give us the equivalent force system to what we had before. So we'll do an example where the shear is applied at the shear centre, and then I'll show you how to actually calculate the location of the shear centre. And the example I've actually put up in the notes this morning. So if you do have an electronic copy of OneNote available, you can follow along. If not, you can just follow what I'm doing on the board. Okay, so we'll do the problem that we had on the board earlier, a box with two flanges off the side, and I'll pre-idealize it, so I won't make you go through the idealization process. So let's number 1, 2, 3, 4, 5, 6, and we'll assume that B1 equals B4 equals 1 inch squared, B2 equals B3 equals B5 equals B6, which equals 0.5 inches squared. And the T, if we need it for all panels, is 0.5 inches. Now, we've got a nice symmetric problem. We don't need to calculate the centroid because the boom areas at the top and bottom are the same and their locations are the same. So what's the first step? And it's the first step in all of these problems. IXX, yes. Sum of by squared. So because it's symmetric, I'll just do the 2 times the top half. 2 times 1 times 10 squared. Sorry, I haven't put dimensions on this. These are 20 inches on every side of the box. Okay, so we've got B1 times y1 squared, B2 times y2 squared, B3 times y3 squared, and we've multiplied it by 2 because we know it's the same top and bottom. Now, our general shear flow equation then is going to be Q2 minus Q1 equals minus SY on IXX, sum of BY, okay, or just BY. If we're doing a subtraction here, we don't need to include the sum. So let's apply a shear force to this. And I'll apply a shear force of 4,000 pounds. And I won't specify where it's applied other than it's applied at the shear centre. So if it's applied at the shear centre, what does that mean for the rate of twist? 0. Okay, we'll use that later on when we need to calculate our QS0, we'll use that fact that it's applied at the shear centre. Sorry, that's helpful. So if we looked at our problem up here, if we started at 3, we could actually calculate the shear flow in panel 3.2, and we could calculate the shear flow in panel 6.5. But once we get to that junction at either 2 or 5, we run into a situation where we've got an unknown. We end up in a closed section. There's an unknown shear flow in our closed section. So what we have to do then is make a cut once we get to that stage and work out our Q basics, our QB, then we work out our QS0 and we can solve. The trick is that we just need to make sure that we get all of our equilibrium right once we get to those intersections. So let's calculate the bits that we can. Q32, and remember that the subscript here matters. 3.2 is the order in which we're doing the calculation. Not only is there a magnitude on shear flow, but there's a direction. If we had Q23, it would be the negative. We'd be doing the calculation in the other direction. Q32 equals minus 4, I'll write out the proper symbols first. Minus SY on IXX, B3, Y3. Minus 4,000 on 400. B3 was 0.5 and Y3 was 10. So we get minus 50 pounds per inch. Now from symmetry, what's Q65 going to be? It's going to be positive 50 because the shear flow goes around the section from bottom to top. So from 6 to 5, we're going to end up with 50 pounds per inch. Now we get to this stage and we've got to make a decision. We've got a closed section. We can't calculate any further because we'll have an unknown Q25 and an unknown Q45. We can't go any further in our calculation. So what we have to do is we have to make a cut, and in the notes I've cut panel 2.5. So QB 2.5 equals what? 0. Okay, we better not put that too high because we won't be able to see what we're doing up there. Okay, so now the section looks like this. And we know we've got a shear flow acting like that already. we've got one in here that we've cut that's 0. So we can start working out the QBs around our loop here. QB 21 equals Q32 minus SY on IXX B2 Y2. So I've got minus 100 pounds per inch for QB21. Now I'll ask you guys to work out what the equation for the next one is. So the next one we've got to work out is QB14. Now based on this notation up here, what am I going to need? QB21 minus SY on IXX. And what B's do I need in here? B1, Y1. Yep. Now I won't do the substitution, but you're welcome to do it if you'd like. We end up with minus 200 pounds per inch. Now I'm going to put some numbers on here just because I'm going to put this above the others. So I'll just number this up. Okay, so what are we left with? QB45. What's QB45 going to be without doing any calculation, just by looking at, minus 100. So if we keep going in the same clock direction, the signs will stay the same. Question? No? All right. So we've now got some basic shear flows. We've got some shear flows that we've worked out properly in the open section. We've got some basic ones. The bit we need is the value of the shear flow where we made the cut. We're chasing this QS0. Now, there are multiple ways of getting at QS0 depending on the kind of problem that we've got. So we can either solve for moment equilibrium, can we apply moment equilibrium in this case? No, because we've got the force applied at the shear centre. We don't know where the shear centre is. We haven't done that calculation, so we can't use moment equilibrium. What's another way of getting QS0? Yeah. Okay, if we assume because our force is at the shear centre, the rate of twist equals 0. So this d theta dz is equal to 0. Now, rate of twist is a little bit tricky in this case because we've got closed and open sections together. But what we make the assumption that the rate of twist for the open sections is large, so we're only concerned with the closed sections. So if you were writing this in a problem, you would say neglect torque contribution from open section. Therefore, the form of the QS0 calculation that is most applicable to us is this one, where as long as we're doing these in the same direction, QS0 and QB in the same anti-clockwise direction, then the sum of QBS over the sum of S will give us QS0. Now, in the general version of this formula, there's GTs and other things that hang around, but we're assuming all of that's constant for this problem. So all the other terms drop out of the equation. So let's expand upon this. We'll keep our minus sign out the front. QB, I better make sure I've got my things in the right order. I'll just say 5.2 times 20 plus QB 2.1 times 20 plus QB 1.4 times 20 plus QB 4.5 times 20 all over 80. So the sum of all the loop. So this is 0. QB21 we had up there is minus 100. QB14 is minus 200. QB45 is minus 100. So when you put all the top together, you get minus 8,000 times minus 1 equals 8,000. So you end up with plus 100 pounds per inch. I'm sorry for writing that in green. I'll write that in red. Now what does the plus sign mean here? Which direction did we do our calculations in? In an anti-clockwise direction around the loop. Okay? So because we did this in an anti-clockwise direction, QS0 is also going to be in an anti-clockwise direction. So we can add that to all the other QBs that we have up there to work out our actual Qs. Actually, I'll put that one up. So Q21 equals QB21 because we're in the clockwise direction plus QS0. So what have we got there for Q21? 0. Q1 1,4 equals QB 1,4 plus QS naught. We've got minus 100. Q45 equals QB 45 plus QS naught, which equals 0. And Q52 equals QB 52 plus QS naught, which equals 100. So let's draw a diagram of what that looks like. It's always helpful to have a diagram at the end. Oh, sorry, they're 50, yes. Okay. So we see that we don't necessarily get the shear flows equaling going in and out of the joint because the boom is carrying some force as well. But the shear flows are all heading in the direction we'd expect them to be heading. Okay, we've applied a vertical shear force, so we expect our shear flows to be generally heading in the vertical direction. So that example is written up in the notes, so you can follow that at any stage. Now at this stage, for this question, I didn't address how to calculate where the shear centre was. I just said we're applying it at the shear centre. In a general problem, what you've got to do is, if you've got a position for your shear force, you've got to work out the shear centre first, move your force from where it was to the shear centre, and apply an equivalent torque to get to the same force system. So if the problem had instead said that your force was applied here, what you have to do is work out where the shear centre is. Let's assume it's, say, 6 inches from the front. Move your shear force to the shear centre. Sorry, that pen's dud. Move your shear force to the shear centre and apply a moment of 4,000 times 14 to get to the same force system as we had before. So we've moved the force 14 inches, so we need to have a moment that gives us the same force system as we had before. And then you would solve the shear force and the torque bits separately. So the torque bit and the shear force bit you would add to one another. The torque's very easy. We know that's just reacted in a loop around the closed section. The shear force, we have to go through the process we just did then, and then we sum those two things together. But the calculation of where the shear force is not particularly easy. First, we assume we've got an arbitrary shear force applied at the shear centre. We cut and calculate QB for the entire section like we just did. We find QS naught for that particular problem using the equation we did here, and then we can solve for moment equilibrium about a given point to work out where the shear centre is. So the finding the shear centre actually solves half of this problem in the process. but you've got to apply another moment equilibrium at the bottom to find out where it is. Once you know where it is, you know how far you've got to move your shear force, so you know what torque you've got to apply. So a follow-up problem that I'll set, and I haven't written it in any notes, but I'll set it now. A follow-up problem, assume that you've got your 4,000 pounds applied at the center web, and try and work out what the shear flows are in that case. So you've done up to nearly at the bottom there. You've gone this far. Now you've got to work out where the shear center is using this. Once you've found out where the shear center is, you know how the moment you've got to apply. You can work out the torques from that, or the shear flows from that torque, and then add the two together. So you're already up to this stage, just do the next couple of steps. Okay, so that's it for open and closed sections. We'll move on to another section now. No, so the torque generates another set of forces. So what you've got to do is then solve two problems independently. You've got to solve this problem where it's at the shear center. And you've got to solve this problem where it's 4,000 times an unknown distance. You'll only know the distance once you've calculated where the shear center is. And then you'll get shear flows in this problem, which we just calculated. You'll get shear flows in this problem, and then you add those two sets together to get the resultant. Okay. So they're independent, and then you add the two together. Okay. Yeah. Okay. So we're going to go one step more complex now, and assume we've got two closed boxes side by side. So instead of having a closed section and an open section, we've got two closed sections, or n closed sections, an unknown number of closed sections. Now, bending of these problems is exactly the same. Bending in all of these cases is exactly the same. For bending, all you need to be able to calculate is the IXX, and you need to know the bending moment on the section, and you can calculate the bending stresses. So bending's not a problem. And this example is from Megson, and I'll just tell you what page number it is. It's page 655. Okay. So in this problem, and I won't go through this problem because it's reasonably simple, you've got boom areas 1, 2, 3, 4, 5, 6. You've got locations of all the booms, and so you can work out IXX from sum of by squared, then work out your stresses from my over IXX. It's a very, very simple problem. Things get tricky when we start applying other loads, torques and shear forces. In general, this is a general problem here. We could have, say, n cells, and this might be, if, for instance, something like a fighter jet. They have multi-spar wings generally because they're low aspect ratio wings. They very low thickness because they fly supersonic. So they generally, instead of having a couple of spars and some stiffeners, will have lots of spars. So you'll end up with these lots and lots of these closed cells side by side. In a more realistic wing problem might be something like this one here. For a large wing where you'll have a leading edge section, a front spar, a main spar, and some kind of dummy rear spar. That might be a more realistic wing problem for a large aircraft wing. So we end up with a few unknowns in this case because we know that the external torque is reacted by internal shear flows in each of the boxes. And because we've got n boxes, we can actually sum those up. So the external torque is equal to the sum of 2AQ, where this QR is all the little Q's inside. So Q1, Q2, Q3, etc. If we sum all of the areas times Q times 2 up, we end up with the external torque. Now, for a one-cell problem, we can solve for Q because we've got our external torque and we've got our Q, we can solve. But when we've got two or more, we've got too many unknowns. We've got one equation here and we can only solve for one unknown. So if we've got 2 cells, 3 cells, or n cells, we're lost. We can't use moment equilibrium to solve the problem. What we need to rely on is rate of twist. And what the assumption is that the section doesn't deform internally, so that when the whole box rotates, when the whole beam twists, every cell has the same rate of twist. So if we calculate the rate of twist for one cell or the rate of twist for another cell, they will all be the same. So we end up with a bunch more equations here. For every cell, we get one of these rate of twist equations. So we start with one equation and n unknowns. When we add the rate of twist, we end up with n equations, and we add one more unknown. And that one more unknown is the actual rate of twist. We don't know how much it twists, we just know that they all twist the same amount. So we now end up with a system of simultaneous equations where we've got n plus 1 equations and n plus 1 unknowns, and we can solve. So in general, that has to be done via a matrix method or some kind of matrix inversion. But for simple problems where we've got 2 cells or 3 cells, we can do it simultaneously by hand. That's not beyond our capabilities. The trick is to work out what we actually mean in our rate of twist equation. So our rate of twist equation here has an integral around each loop. So if we go around loop R of Q times the length that we're going on T, and we could turn that into a sum as well. We could say that we had, instead of this integral here, instead of the integral of Q ds on T, we could have equals the sum of Qs over T. Okay. When we've got panels where there's no variation in shear flow as we go across the panel. So if we've got a constant, this is just somewhere in the middle of our section. We've just taken a piece out and we'll call it cell R-1 on the left. cell R and cell R plus 1. Now the rate of twist for cell R, which is this subscript that I've got here, is equal to 1 over 2 times the area enclosed by R, so this area here, and we need to know the shear flows around the loop. Now the shear flows around the loop, if we go from panel 1 to 2, we've just got QR. But if we go from 2 to 3, we've got a contribution from QR, or from the R cell, but we've also got a contribution from the R minus 1 cell. So from panel 2, 3, we end up with QR minus 1. Which is here. Panel 3, 4, we're back to QR again. And panel 4, 1, we've got QR minus QR plus 1. So the notation that Megson uses for this is written here, where these little deltas are equal to S over T for any particular panel. Okay? So delta Ij equals Sij over Tij. So if you see delta 1, 2, delta 2, 3, delta 3, 4, so if we go around the loop, if we start at 1, 2, we get QR times delta 1, 2 plus QR minus 1, delta 2, 3. So we've gone this one, then across the bottom, and then up the right-hand side. So we've gone around the loop here. We can rearrange that a little bit, and we get all the QR minus 1 bits together, all the QR bits together, and all the QR plus 1 bits together. So we've just rearranged the order of the terms here. We've moved terms in the middle to the left. We've moved this term to the left, and we've moved this term to the right, and all the others we've collected in the middle. Now Megson makes another little notation quirk here, which I'll explain because it confused me when I first read it too. Delta I is equal to the sum around the loop of delta Ij. Okay? Actually, I'll change my notation there. Don't write that down. Delta R equals the sum over the loop R of the internal deltas. So he's just saved himself some typing really. He didn't want to write it all out in the equation editor by condensing this whole bit into a single term. So confusingly, but I'll use his notation just because the tutorial questions and everything you do are in his notation. Let's do a problem to illustrate. Okay, and I've got to get a little bit more information for this slide. This is example 23.3 from Megson. And the additional information that you'll need, well, there's quite a bit of it, but I'll I'll put it up on the slide projector, is probably the best. On the document camera. And then projector warms up. Okay, there we go. Hopefully that's readable from the back. But if you've got a copy of Megson, you can copy it straight out. So let's copy all these down and I'll explain what they mean as we go along. So here he's got a numbering system for the walls of the cell. So 1, 2, little superscript O means outer. So 1, 2 outer is the outer part that's got numbering 1, 2. 1, 2 superscript I is 1, 2 inner. So it's the wall here. So just for the video, this is 1, 2 outer. And this is 1, 2 inner. And the other numbers are all self-explanatory. The length of every boom is here in the table. The thickness of every panel, not boom. The thickness of every panel is here. The G, let's not worry about varying G unless you're trying to follow Megson exactly. Let's just all assume that the top value of G is constant throughout, because by changing G makes our calculations really tricky. And the areas of each boom, of each cell, are here. Where a cell is the area inside one of these boxes. So this is AI. And the external torque that we're going to apply is shown here on this slide, which you should write down as well, which is, if you could draw down the geometry, because I'm going to move off that slide. So the first thing we generally do with this problem is calculate all our deltas, because our deltas are just going to appear in all of our equations, so getting rid of them early helps us out a lot. Okay. So what we'll calculate is the delta for each wall, and you can do this in the table. So delta is just length over thickness, so you can just add another column in your table for your delta. You can also add another column after your cells to work out your deltas for your cells. And And I'm just going to erase all my annotations off here. So let's just do a couple of examples. What's delta 1, 2 outer? It's 1650 divided by 1.22. 1, 3, what was it? 53. And delta 1, 2 inner? 250. Huh? Democracy? What was 250? Okay, and what units are they in? Nothing, dimensionless. Okay. We can also work out the D's for the particular cells because we're going to need to go around each loop. So delta I is equal to delta 1, 2 inner plus delta 1, 2 outer. Delta 2 is equal to delta 1, 2 inner plus delta, I haven't got my numbers up there, 2, 4, then delta 4, 3, and then delta 3, 1. Okay, so we're just adding up around the loop. So let's set up the equations that we'll need. So how many, if we're going to solve this, how many equations are we going to have? And how many unknowns? We're going to have one torque equation, and we're going to have 3 rate of twist equations. We're going to have 3 unknown shear flows, constant shear flows, and we're going to have 1 unknown rate of twist. And the rate of twist in the end doesn't really bother us too much for this problem, but if we needed to know the rate of twist for the whole section, we could solve for that as well. So let's go about setting up the equations that we need. Now, has everyone written this down? I'm just going to clear this now. So the external torque equals, what have we got, 2 times the sum of AR, QR. I've just taken the 2 out the front. And in this case, we're just going to have n equals 1 to 3 because we've got 3 cells. A1, Q1 plus A2, Q2 plus A3 Q3. Okay, another little trick when you're reading Megson, if he uses Roman numerals, he's referring to cells. So he's referring to shear flow for things to do with cells instead of for particular panels. So what in this equation do we know and what don't we know? So we know this, we know this, we know this, and we know this. So we've got three unknown shear flows. So we need at least two more equations, and it turns out we need three more equations to solve for those unknown shear flows. So we turn to rate of twist for cell 1. Rate of twist for cell 1 equals 1 on 2A1 G. Okay, remember we've got a constant G everywhere. If G wasn't constant, it would have to end up inside the sum as well. Sum of Q times S over T. Which is expanded here as okay, hang on, I'll write this out in the notation that we're actually trying to write it out in. Okay, so cell 1 in our problem is on the far left-hand side. There's nothing else impacting on it. So this term here disappears. There's nothing on the left-hand side to influence it. So let's write out the next term, Q1 delta 1. Minus Q2, where QR plus 1 is the cell to the right, so it's Q2. Now, delta R plus 1 R is the delta for the wall that's common between R plus 1 and R. So in our case, what's that wall? Between cell 1 and cell 2? Delta 1, 2 inner. So what have we done here? We've introduced this new unknown. We don't know what this one is, but these, sorry, that has to be a question mark. We don't know what our shear flow, our rate of twist is, but everything else in here we're happy with because we've got an equation for them above. Okay, so we've only introduced one more unknown. So we've now got 1, 2, 3, 4 unknowns, and we've only got 2 equations. So we need to keep constructing equations. d theta dz 2 we've got minus Q1, and then delta R minus 1 R is the wall between R minus 1 and R. Which is delta 1, 2 inner. Okay. Plus Q2 delta 2 minus Q3. What delta do I need here? 3, 4. So have I introduced any more unknowns into this equation? No, because we've assumed that these two are the same. So there's no new unknown there. And everything else, there's no new unknowns. So we're closer. We've now got 4 unknowns and 3 equations. And we need one more. Okay, so I've just written it out without asking for any proof. We've got the contribution from cell 2 and the contribution from cell 3. So now we've got 4 equations, 4 unknowns we can solve. Now, a 4-term or 4-equation simultaneous equation is not the easiest thing in the world to do. There are some tricks. Once you've done a few of these, you can work out what terms to sub in to get rid of certain things. The first thing in most problems you want to get rid of is the rate of twist, because the rate of twist is less interesting to us than the shear flows that are in the section. So Megson doesn't show the simultaneous equation solving for this problem. He just says it can be done. The example in the tutes is only a 2-cell problem. And so 2-cell problems, you've got 3 equations and 3 unknowns. It's something that you can possibly do by hand. In practice, if you were doing this for a complex problem, what you would do is set up a set of equations where you had something like A Q1 plus B Q2 plus C Q3 plus D d theta dz equals 0, or equals a constant, sorry. I'll give it another one, E. And then you'd have another equation, F Q1 plus G. And so you'd end up with 4 of these. And you can make a matrix solution. And once you've got a matrix solution, you can solve it with any numerical solution package. Okay. So you have some terms, which are all your constants here. You have your unknowns you're trying to solve for, and you have your right-hand side bits, which I've written as C1, C2, C3, and C4 for the sake of this. But all your terms end up in here. Okay, so for some of the tube problems, you would have had some experience potentially making matrix solutions for composites. You can also do matrix solutions for any set of linear equations like this. Okay, so unfortunately torsion was the easy one. Shear, it gets even harder again. For shear problems, we need to cut every section. We know that we can't solve these independently, so what we do is we can't solve them from the shear flow formulas alone. We have to have open sections to do that. And what we have to do is take a section and go along and cut everywhere. 1 cut, 2 cuts, 3 cuts, 4 cuts, 5 cuts, 6 cuts, whatever, n cuts. So what we end up with is Q, Megson's notation is QS naught N, or R, where he writes this as R. Okay, we end up with n of those. And we use the same solution process. So we cut everywhere, we solve for QB. Once we've solved for QB, we can work out the rate of twist for every section. So the rate of twist for every section is the same, except inside now, we don't know our Q's. We've got a QB plus this unknown constant shear flow. So our equation looks very similar for the first bit. This is the constant parts. But then we have the basic parts as well. So here we've got n equations, but we've got n plus 1 unknowns. Because we've got an unknown, we've got n unknown constant shear flows, and we've got 1 unknown d theta dz. So we need one more equation to be able to solve this problem, and it's the same equation that we used for torque, just written slightly differently. So what's the equation of statics that we need to resolve this? We've used rate of twist, moments. Okay. So the external moments on the left, the internal moments on the right. The internal moments are separated for every cell. So we've got the moment from cell 1 plus the moment from cell 2 plus the moment from cell 3. Each one of those moments is just the Q in the loop times PDS. So this is our integration around the loop. And you've got to do that n times. And if you rearrange, you end up with your moment equation having a basic part and a constant part. And if you're paying close attention, this constant part is exactly the same as for the torques. Slightly different subscripts, but we've got the same equation there. Okay, so the complication with shear is that we've got to add the basic parts as well as the constant parts. So I'll see if there's an example that I can go through in Megson that we can do quickly in the next half an hour or next little while. Actually, I might leave that example for a tute question because there is a tute question that's a simple example. I'll follow on with the rest of the lecture material because there's some important stuff I want to cover. So I'll leave that question, that example for a tute. Okay, so this is one example from Megson, which you can do with shears. If you put a shear force on this, you can work out the shear flows around the section. There's a tute question which I've recommended, which is a simpler version, which is symmetric. That's just a 2-cell problem with some booms like this, I think. Okay, I think that's question 23.5. Which I suggest you do as a good introduction to this problem. Okay, so now we've really got ourselves to a stage where we can handle most wing calculations. So if someone threw at you a cross-section of a wing that looked kind of realistic, like some of the ones I've shown over the last few weeks, and even though I said it looks realistic, my drawing won't look realistic. Although it would be computationally tricky, you could solve this problem. If someone said, I'm going to use this as my wing and I know my lift from my aircraft. Once I know the lift from the aircraft, sorry, that pen's dud. Once I know my lift, I can work out what my shear force and bending moment diagrams look like. Okay, so at any point you can work out what the shear force and the bending moment is in the wing. So you can apply a shear or a bending to this problem, and you can idealize. Now, we can idealize this problem. And once you've idealized it, you know how to go around and calculate the shear flow in all these panels. You can make a cut, you can solve QB around the loop. It's not an easy calculation, but you've got all the steps you need to go through that kind of problem now. So I want to wrap up this general topic about booms and panels, because next week, although it's an analysis topic, it's a different challenge. We're talking about joint. So this is really the last opportunity we get to talk about this kind of idealized structural calculation. Almost all of the stuff we've done at the moment is looking at sections. So we've really looked at things being constant extrusions of the one section, and there's a section in Megson to account for taper as well, if we want to account for taper. But they're really kind of quasi 2D problems. They're not really 3D in any real sense. So what I want to do is look at how we would handle more three-dimensional problems. So if we had a force that was applied at the intersection of different booms in 3 dimensions. Now, the first principles, the assumptions that we make, are that thin skins don't carry high compression loads. So they can carry, where's my analog of a thin skin? So this is my thin skin analog that I've used a few times. So they can't carry very high compression loads because they'll buckle in and out of plane. They can't carry transverse loads very well, so if they will just deform under a transverse load. And they can't carry point loads. So if I grabbed a small little point and pulled on it, I would just tear through my skin. I need some stiffened structure around the outside to introduce point loads in. Now, stiffening members, we assume if they're around the outside or in the middle, carry direct loads but don't carry anything else. So we could set up a problem like this, where this is just a deep beam at the moment, but we could imagine this being say a spar web or a rib where we've put some internal stiffening members in, and we'll see in a few weeks why we might want to put some internal stiffening members in. But we can do more complex calculations than the simple 2D problems that we've done here. We can assume that there's some shear flow inside our structures, and this is a 2D problem, but we can generalize to 3D as well. So I'll show you what I mean with just a pure numerical example. So what we've got here is called, say, a deep stiffened beam, is what Megson refers to it as. And we've got flanges and stiffeners around the outside of panels. So these panels are solid. There's not a hole there anymore. There's actually material in the plane of the problem. All of these before, if we drew this, we would think that there was holes there. Now there's actually material. There's a shell that's sitting like this. It's actually carrying our shear forces. Okay, and we denote that in problems by drawing these internal shear flow pictures. So if you see one of these in a problem where someone's drawn these little internal shear flow diagrams, you know that there's actually material there. There's not meant to be a hole. Okay, the task of a problem like this would be to work out what the forces in the flanges was and what the shear flow in the panels was. So another example this could be is part of the wall of a fuselage. If you had an attachment point for some kind of tie-down strap, or at the bottom some kind of mass or landing gear, coming in through a frame. Each of these panels might be a skin panel, and then the flanges might be a frame or a stiffener. But we could build this up as complex as we wanted to, but we'll start with a simple example like this one. So what we can do at any point, we can take slices and look at equilibrium. So let's do that for the whole section. Now the way to read these little pictures of shear flow here, they have a little arrowhead on all of them. And what that arrowhead means is if we make a slice and we need the shear flow on the left-hand side of the slice, the arrowhead tells us the direction that it's going to be acting. So we've made a slice through our panel just inside the wall. So there's going to be a force on this side, or a shear flow on this side, which is equal to Q4 times the height, which is 300. So the thing that's carrying this up vertically is the shear in this panel here. So this is Q4, this is Q3, this is Q1, and this is Q2. Now, we've also, if we pull down on this, what's keeping the bending moment equilibrium? What's stopping this spinning around on the board? We know that these panels can't carry direct stress. There's nothing that can be carried there. So we've got some direct forces in our flanges. Okay, and I'll call this PA and PE, just to denote where they are on the section. So we've got three equations of equilibrium. Sum of forces x, sum of forces y, and sum of moments, where we'll say x is horizontal and y is vertical. And sum of moments we can take about anywhere, but the easiest place to take it about is somewhere that cancels out one of our unknowns. So if we take it about E or A, So for this example, we'll take it about E. So sum of forces in the x direction, we have 4,000 sine 60, which is the horizontal component of this force, plus PE minus PA equals 0. Sum of forces in the y direction, 4,000 cos 60. Sorry, that's minus 4,000 cos 60 plus 300 Q4 equals 0. Oh, sorry. Yeah, I've got another minus 5,000. I missed a force completely. Okay. And sum of moments about E. Okay, so if you notice here, we can solve for this one straight away. That's not really a simultaneous equation. We've got one unknown and one equation. And the sum of moments about E will assume anti-clockwise positive. So PA times the distance to PA, which is 300, minus 5,000 times the distance, which is 250. Now we'll break the 4,000 up into components. So we'll have a clockwise component from the x part. So minus 4,000 sine 60 times 100. And a clockwise component from the y part, minus 4,000 cos 60 times 750 equals 0. So again, this isn't really a simultaneous equation because the only unknown is the force A. So once we've solved for PA, then we can sub it back in here, and we can solve for PE. So that's one way of doing this kind of problem. We can take slices anywhere we feel like and work out what the equilibrium on those slices is going to be. So that's the equivalent of doing, say, a method of sections for a truss. Okay, so you know your truss calculations. If you've got the whole truss in front of you, you've got a force applied somewhere, you can just cut the truss and work out based on where your cuts are what the forces in the members are. And that's what we've done here. This is a method of sections. What I'll show you now is a method of joints, another way of solving the same problem. Now this method relies on the assumptions we said on the previous slide, that our skin can't take transverse loads or point loads, and that stiffening members only take loads in the direction that they are carrying them in. So if we wanted to, for instance, look at joint K, so where that force is applied at K, now what our assumptions tell us is that all of the load that's externally applied at this joint, the x component has to go into jk and the y component has to go into dkh. The y component can't go into jk. Now what we also know is that at the ends here there's nothing else to carry load, so that the boom loads at the end here have to go to 0. So there's no forces hanging off the end. So how do we maintain equilibrium on this? Well, we maintain equilibrium with the leftover shear flows that are there. So we have Q1 acting on that wall. Imagine we just cut out the majority of the panel and just left the slightest little bit of panel around the outside. We've got Q1 acting on that wall. We've got Q1 acting on that wall. We've got Q2 acting on that wall. And Q2 acting on that wall. Now, has anyone got any queries about the direction that I've chosen for those? Okay, see, in the diagram we've got here, I'll draw a white slide version of it. We had our shear flows acting like this. Now, when we read this diagram, this tells us if we cut somewhere, then the shear flow acting above the cut will be to the left, or if we cut somewhere, the shear flow acting on the outside of the bottom of the cut will be to the right. What we're actually doing is we're cutting out most of the panel, but leaving the slightest little bit left over. So there's a little bit of, an infinitesimally small little bit of panel left there. So we have to use this direction as an equal and opposite force set up in here. Okay, those two are equal and opposite to one another. Okay, so if we've made a cut, we use because the cut, there's got to be a little tiny bit of panel left over, we use the top side, and the same for Q2. We have to go in that direction. All right. So I've left a little bit of information off here. These aren't forces yet. These are just shear flows. To get the forces, what do we need to do? Multiply by lengths. Okay. So our length here is 250. The length of the top bit is 200. And the length of the bottom bit is 100. So let's set up our equations. Sum of forces on boom JK equals 0. So 4,000 sine 60 plus 250 Q2 minus 250 Q1 equals 0. We've got two unknowns here. Sum of forces on DKH. Now we can't do these independently because there is going to be some force transferred at K. So we have to treat DKH as one big piece. Minus 4,000 cos 60 plus 200 Q1 plus 100 Q2 equals 0. So again, we've got the same set of unknowns here. So two equations, two unknowns we can solve. So in this case, I'll just see if I can find the section in Megson quickly. He gets Q1 is 11.3 newtons per millimetre, and Q2 equals minus 2.6 newtons per millimetre. Now one last thing before I let you all go. This method is very good for finding the shear flow in the panels, but we can also find the forces in the flanges as well. So if we look at boom JK, then on this end of it, we've got 4,000 sine 60 pulling this way. On this end, we've got nothing. So there's got to be a variation in force as you go along. And the way to find that variation in force is that your Q's, and I better get the direction right, if we took a section and wanted to work out what the internal force was, we can solve because we know the external force on one side We know the shear forces on the sides based on the length of our little piece, so we can work out the force on the other end from equilibrium. So the force has to start at 4,000, it has to end at 0, so in this case it's just going to be a linear drop from 4,000 sine 60 down to 0. But there's a very nice example in Megson that I urge you to have a look at, which is at the start of chapter 24, which goes through this whole problem and works out all the forces in all the flanges and all the shear flows and shows you all the different techniques, method of joints, method of sections to solve.